Hi everyone. So this is going to be the last video of the series of the embryology series, and this should be covering most of everything that you need to go over. I will say though, I believe in the chapter 6, there are a few portions that I haven't covered, which are like development specific timelines. So like which at what week does your brain like does the eye form or does your do certain features form? They're like on a picture at the top. I didn't really go over that because there's not much to go over. It's a lot of brute memorization. Um and I also didn't go over a few statistics because statistics, I feel there's not much like benefit in going over. You guys should read over the book and just make sure that you know the statistics. I didn't get too many questions on statistics in my brain bee as well as in the national brain bee, but it's always a good thing to know. Just go over them a few weeks before the competition just to kind of get them down. But other than that, I kind of covered the main gist topics that are really important and are often really hard to understand just by reading. And again, I did say this in the last video, but I just wanted to say it again. Learning this in 2D and just listening to a lecture or just reading a book usually is not enough. Watch a video. I'm going to publish a series of videos that I found really helpful while studying for this. But at the same time, do your own research, kind of figure out, look at websites, look at animations of this process, because if you don't understand and you can't visualize it, it's really a lot of memorization. So don't try to limit memorization as much as possible. Understand the logic behind it by watching animations and trying to visualize the process instead, if that makes sense. If so, basically, how I kind of when I explain this process, I'm visualizing and I'm tracing every step. And once you see it happen, it makes a lot of sense as to why it happens like that, and you gain a lot more appreciation for the subject. Okay, sorry, that was my little rant, but let's get started on the contents of the video. So in the last video, we covered the closing of the neural tube, right? We remember how the cranial end closes slightly faster than the tail end, your caudal end, and this happens on day 25 to day 27, right? So what happens if the neural tube doesn't close properly? So basically, first let's go over what happens more specifically if the head end doesn't close. So anencephaly refers to when the anterior neuropore, which is the more formal tube for the head end of the neural tube, to that doesn't close properly. So it doesn't completely shut, or it may partially shut, may partially not shut, right? So the anterior neuropore, when it doesn't close properly, first think about what's going to happen. Why does the neural tube need to close? Well, if it closes, then what's going to happen is it allows for your brain and your skull to develop properly. But if it doesn't close properly, then that's going to expose the brain and the skull, and it's not going to allow it to develop fully. And oftentimes, what this results in is your brain, parts of your brain is not developing, or when you're born, actually completely being exposed to the world, right? And obviously, we understand why that's problematic if your brain doesn't develop fully or missing important parts for your function, as well as exposing your brain can cause a various amount of infections that could become septic, and even just not having protection allows for a lot more easier access to the brain, so to form contusions. So what does contusions means? Contusions means bruising. That often can lead to degeneration of neurons on its own, and it's really, really harmful. Basically, what you need to know for this is that anencephaly is when your head end, your anterior neuropore, does not close properly. What this results in is your brain being exposed and your skull and your brain not forming properly. This will result in intellectual disabilities. I'm going to abbreviate that as intellectual disabilities. Ha- and often high mortality risks, fatality risks, and is often not compatible with life. compatible with life, right? And now let's go over spina bifida. So this is what happens when your tail end doesn't close properly, or your posterior neuropore, which is the tail end doesn't close properly, right? And the reason why this is so important is because spina bifida is actually a little bit more forgiving than anencephaly, right? Because anencephaly is the brain. It's like crucial for living. With your basic functions, everything is controlled by your brain. But your spinal cord is a little more forgiving than that. Um, Needless to say, it is very important. Like it's the communication from your brain to your body. Like if that's damaged, it's very risky. But at the same time, it's slightly more forgiving than anencephaly. And you'll get what I mean by that by looking at these examples. So first, let's start off from spina bifida occulta. Spina bifida occulta is basically a slight malformation in the spinal cord, right? So there's like a little bit that didn't develop properly, and that just causes it usually doesn't cause any hindrance. I think for spina bifida occulta, the only sign is basically a little bit of hair on and like a little white spot on your spine on your back. But other than that, there really isn't a spina bifida occulta. And oftentimes, I think the only complication could be like a buildup of cerebrospinal fluid, which people put shunts to drain the fluid out from. That's a little bit beyond your pay grade, but spina bifida occulta is basically just a slight malformation. Slight malformation. And I think a hallmark symptom of spina bifida occulta that actually the Brain Facts book doesn't mention, but it's important to know is small patch of hair. Small patch of hair on your back. And then meningeocele. Meningeocele is basically when there's a small outpouching from the spinal cord, right? So basically, in your spinal cord, you have kind of a cavity that surrounds it. And what happens is that cavity kind of bulges outwards. And honestly, this is a little problematic because you're going to put a little bit of pressure on the spinal cord, and it's it's like filled with cerebrospinal fluid. So it's kind of just a fluid-filled pouch that bulges out from your body. And this is meningeocele. So your meninge, remember your meninges are the three tissues that kind of line your brain and your spinal cord. Your meninges kind of bulge outwards from your body. So there's going to be a little pouch outside your body. This is problematic because it exposes the pouch and it's often susceptible to infection really easily, but I think I'm pretty sure it's compatible with life. But the most common and the most fatal form of spina bifida is what's known as myelomeningocele. And you'll understand why this is so dangerous if you break down the word. Myelo, brain, or myelo usually translates to something relating to the brain and the spinal cord. Meningeo, which translates to meninges. Seal, pouch. Brain or spinal cord, tissue, pouch. So, quite literally, what happens is your spinal cord will and your matter will form outside in a pouch of your body. So you can literally see how here your spinal cord formed outside of your body. This is your body. This is forming outside your body. And this is so very dangerous because what if this is basically exposing your spinal cord to massive potentials for harm? if the pouch pops, or say the pouch gets infected, or say that there's also a lot of strain that's happening of the spinal cord when it grows outside of the body, like it's stretched in ways that it should not be stretched, and often this results in very, very harmful consequences and is not compatible with life, unfortunately. So this is the most dangerous, but you can do surgeries, I think, to fix it, but it's very fatal and you have to catch it very early. This is actually caught in fetal ultrasounds, I believe. So this is another reason why you guys should really advocate for anyone to get regular ultrasounds, because this can be treated, but only if caught early. All right. So that was a little bit of examples of everything. I hope it was clear. And now let's go into neuron formation. So basically, let's take a cross section of the neural tube, which basically means I'll cut it down this way. You're going to see three layers. One is your ventricular zone, your mantle layer, and your marginal zone. So your marginal zone is kind of like your cerebral cortex, the outermost layer of your brain, right? Your mantle zone is kind of like that gray area, or like your white matter, basically. And your ventricular zone and your glial cells, oh my God, is basically contain a space containing immature nerve cells. So nerve cells that haven't completely gone through that secondary process, right? So we'll talk about that secondary process in this phase, actually. Stages of neuron development. So first, right, you have um, the formation of your the stages of neuron development. Basically, the first step in that is formation slash induction. Sorry, I'm repeating myself here, but your immature nerve cells will kind of aggregate in this zone over here. And what's going to essentially happen is there's going to be a stage in which signaling molecules are released again, right? So that's the phase of differentiation. Basically, signaling molecules are released in different concentrations along the embryo. So basically, there's a mesodermal signaling molecule called sonic hedgehog, which differentiates neurons into either inner neurons or, um, I believe it's motor neurons, or communication. So inner neurons, which are communication neurons, or motor neurons, or glial cells, depending on where those neurons are located in relative concentration. So basically, if there's a oh my gosh, if there's a high concentration of sonic hedgehog near where the neuron is located, it's going to become an interneuron. But if there's lower concentrations, it's going to become a glial cell. Things like that, right? So that's stage 2 differentiation. Once their cells are differentiated, they don't need to be in this arrangement anymore, right? They should move to the place where they belong in the brain. And they can do this via two possible ways, right? So the first way is through radial migration, which 90% of neurons take. So what they will do is they'll move from the ventricular surface, your innermost layer, to the outermost layer. So this is mostly what happens in your cerebral cortex, right? So what they will use are these neurons called, I believe, radioglia, and they're going to literally climb these neurons like railroad tracks to get to where they want to go. So they go from inwards to outwards. Then you have the type called tangential migration, where oh my God, these neurons will migrate from your brain to a different region, but kind of along the neural tube. So if this is the neural tube in to out, it's gonna go kind of inward. So if you extruded this, if you made it into a cylinder like this, it would move out like that. And if you think of examples off the top of your head, the only reason you might have to do this is because of spinal cord neurons, right? Your spinal cord neurons need to reach their proper destination by going down the neural tube, not from inside to out. It's not in your cerebrum, right? literally downwards. So that's why you have tangential migration. So often this is for neurons that have to do a lot of communication with other parts of the body. These often engage in tangential migration. So this is day 21 to 40. Um, a lot of the information that I included on this slide might not have been in the brain facts book, but I kind of wanted to introduce you guys to the deductive reasoning that I used here, right? So this oh sorry. This segment over here, I didn't really, this is not something you need to know. It's part of the anatomy curriculum, which is a different competition that I was just trying to get a little bit of introduction to. But notice how here, when I talked about the formation and induction part, or more specifically the migration part, I kind of used my reasoning here. The book did say that radial migration was the most common, right? So you should try and think, okay, if it's saying from inner to outer, where would I expect that to happen? And then tangential migration, when it's saying it travels outwards or it goes radically, it kind of moves in a direction that it wants to. Where would that happen? So, trying to connect those dots is a very crucial part of med school thinking that we need to start trying to use, right? And a lot of the brain bee questions will be a little bit more conceptual like that. So, which neurons might you expect tangential migration to occur in, right? And obviously, you don't, this was never mentioned in the book, but how are you going to know? By kind of thinking of where these neurons are, how they're found in the body, and which type of migration makes sense for that, if that makes sense. And yeah, that's pretty much it for neuron formation. Finally, errors in proliferation. So basically, I'll give you guys a very, very brief overview of this because I actually need to do a little bit more research before I can give you guys like the final stamp, you know? But this is what I kind of got a gist of. And I haven't fully learned this process either. So I'm going to give you guys a kind of a brief overview of this. Basically, there are two types of proliferation: symmetric proliferation and asymmetric proliferation. Symmetric proliferation is basically a process in which your mother cell, or your father cell, I believe actually, creates two identical daughter cells. And same way, these will produce two symmetric daughter cells. I'm gonna find it slow. Two symmetric daughter cells, a lot like mitosis actually. And what this does is it strives to create a group of cells, right? Like a group of cells that can be used to become specialized, become differentiated, and then travel. Asymmetric proliferation occurs after these cells have differentiated, and what it's going to do is it produces one identical copy, and then it produces another cell that basically just becomes a stem cell or a cell with potential to become another cell. And basically, the goal is to only produce one identical daughter cell in every proliferation, and that way you kind of get enough specialized cells. So it's a more controlled version of cell division, and there should always be balance, right? So what happens if so there's going to be a switch at one point, right? In proliferation, you're going to switch from symmetric proliferation to asymmetric proliferation. And why is that important? Well, think about it this way: what happens if you switch too early from symmetric proliferation to asymmetric proliferation? Well, there's not going to be enough cells to commit asymmetric proliferation in the first place. In other words, when your resource itself, when your base resource is a fraction of the size it's supposed to be, when you only have this much material left, you're not going to be able to produce enough cells, right? You're not going to be able to produce enough um, kind of cells to promote asymmetric proliferation, right? Because these cells will, after that, conduct asymmetric proliferation. In all, you're going to result in less cells than necessary. So that is a phenomenon called as microencephaly, where your head is too smaller than what it's supposed to be. What if it doesn't switch in time? What if you have a very late switch from symmetric proliferation to asymmetric proliferation? What that means is that your asymmetric proliferation, you're basically going to have too many cells to start off with, a way, 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 way bigger pool than what you wanted. And once all these cells will start committing asymmetric proliferation, you're going to have too many cells than what you want, which is a phenomenon known as megaencephaly, in which your brain or your head is too big than what your body can support. Either way, this will result in a lot of intellectual disabilities, basically high risks of injury because one, either in microencephaly, you don't have enough cells, your brain is underdeveloped, or in megaencephaly, your brain is too heavy and can often injure your spine because of all the weight. So basically, those are the two disorders that the Brain Fox book covers: anencephaly, spina bifida, megaencephaly, and microencephaly. Right? So all of these disorders are important for you to know. Just make sure you understand the logic behind them, right? And yeah, thank you so much for watching. And I was also mentioning about the library of resources. As I said in the previous videos, one of the previous videos, I will have them uploaded by the end of this month on June 31st. So please be on the lookout for that. I will post a community update when I have the resource ready. And yeah, thank you guys so much for watching. Have a great day. Bye bye.